Well, good morning, ladies and gentlemen. I will talk about some geotech investigation that you have done in Recife soft clays deposit. Next, please. In Recife plain area, we have more than 50% of the area, we have some type of soft ground deposit. And we have a geotech group since 1998. We have developed a research program in the Recife soft clay deposit, perform a very intensive program of laboratory and in-situ tests for many sites of the plain area. We have main reference here. And for this paper, we prepare specific material about dilatometer test. Next, please. Then the objective is the evaluation of the geotechnical information from Recife soft clay using DMT. Classification of soil types, stress history, in-situ horizontal stress, compressibility, and strength parameters. And you have a second part, practical application in pile foundation, in steel pile under lateral loading, and if you have time, I will show some very recently results in vertical load capacity. Next. Here is Recife, Pernambuco is the state, and that is the plain area. That is the number of investigated sites in soft soil that you have done in our laboratory. And that too are our research sites. Then this presentation will be more directly for that two research sites. Next, please. That is an overview of Recife lowland. We have a very old city, one of the oldest city of Brazil, here, very close. That is the Capibaribe River and the sea. Then the plain area, we have the influence of the river and the sea in the soft soil formation. Next, please. Another general overview of Recife lowland. Next, please. The Recife International Airport. Here is an important area. It's a mangrove, very big mangrove area inside of the plain area. Next, please. Here is one of the research sites, and very close another mangrove area. Next, please. Here we can see some typical soft soil profile in the plain area of Recife. We are talking about these two research sites. The first one here, the second one here. Then we can see some information here of the profile and the SPT number and other type of Recife soft soil profile, including some very organic soil here. Next, please. Here the characterization tests. For the first one, research site, we can see a very high natural water content and the plasticity index, some organic content, and in Recife is very important for us, and we recommend this for the practical people. Take natural water content from the SPT test, because it's very clear, for example here, that we have two layers, different layers, and for the SPT it's not so clear. Next, please. It's the same, the second research site. That case is a very, very soft clay. We can see here. Again, we can see the very difference in the natural water content, and that is very high, and very high plasticity index, and the organic content is here. Next, please. These some dilatometer test results. We can see here the KD, and the close in the second layer is close to number 2. Is completely clay material. It's common in our research. We use the C reading to take the UD pore pressure index parameters. No? Next, please. Next. Sorry, it's the second, sorry. It's the second research site. Then here it's very clear the KD, very similar for the OCR. We can see after OCR condition. And the same here, around 0.7, little higher UD. The same here, in general, is very, very clay material. Next, please. The first geotechnical parameters, we can see soil type in the classification chart, including here the Lacasse and Lune suggestion. Then that is the result of received soft clay. That is the research site 1, research site 2, and the two different layers. Then we can see very, very plastic and organic here material. Next, please. Then the unit weight for the first research site, the second. Then when we have a very soft and organic material, sometimes the DMT unit weight is little higher than the laboratory result. For example, here is very clear. Sometimes it's very good, the results. Next, please. The keynote result. The idea is you use the general correlation to see what is the best correlation to be using in received soft soil. Then we can see the Marquette, the Lune et al. Correlation is the best for keynote here in Recife. The reference results for this case is the proposal of Meiring-Kuihari A2 equation. Please, next. The direct correlation between K-note and KD. Then again, we can see the good correlation. And the idea I will show later, the quantitative comparison. Next, please. Over consolidation ratio, the same, again, many empirical proposal, correlation. Then we can see here that the Lune, again, Lune correlation for using a range for this coefficient, we can see a good result. Next, please. Again, we can see very good comparison. Next, please. Characteristic of compressibility in the M modulus, we can see here for the two research sites, and in comparison of the odometer results. No? Is a little higher the DMT result or very similar results. And it's important to show how is compressible this material. Look at the compressibility parameters is very higher, and in some cases very higher for this, for example, soft soil deposit. Next, please. The coefficient of horizontal consolidation. This is from DMT. This is laboratory test results. And this is the comparison from DMT for one specific site. Next, please. Undrained shear strength. Again, we have laboratory triaxial compression triaxial test. From vein test, the reference results here from Marquette and Lacasse Lune, and we can see the results are very similar in two different sites. Next, please. Here the comparison. Then we can see here is included the Keimei and Yazaki proposal. Is the higher results here. Laboratory and vein, and we can see that the Marquette proposal is very good for the result in general. For the vein and for the laboratory, Lacasse Lune is little better. Next, please. That is the summary of this analysis. The idea is to have a quantitative comparison between the DMT results and the reference test for these 4 different parameters. OCR, the reference is the odometer's test. Then we have here the quantitative comparison. No? Then we can see that the Lund et al., also Power et al. Propose, is very good for practical purpose. Then that is the correlation that we recommend for the practical application in received soft soil. We have a range for this coefficient with 10% minus plus 10% of the derivation, standard derivation. Keynote, we have 2 proposals. We have, in this case, Marquette proposes present very higher result than our reference information, and the recommendation is to use Lund et al. Equation with, again, 10% standard deviation. In the undrained shear strengths, we have 3 equations, and we have 2 different reference tests: triaxial, compression triaxial test, and vein test. Then we have here the Marquette and the Lacasse and Lund, basically the same for vein and laboratory test. Then this is our recommendation. Of course, the Marquette is not so high for laboratory also, but this is the recommendation that we have for received soft soil. And the M, we have around 20% higher, 0 to 20% higher when you use the Marquette equation to get the M modulus. Next, please. Well, then the practical application, we have 2 cases here. The first one is steel pile under lateral loading in a very soft clay. That is for the second one, the research site. It's a very, very soft clay. The research was prompted by a general failure of a concrete structure caused by buckling of a steel pile foundation. Then we decide to make the investigation. That is a consultant work. Then we did a lateral load test in 2 steel piles, and we did an analysis comparing the field results with predicted by linear and nonlinear finite element analysis. And the idea is try to explain why this concrete structure failed after 22 years. Then the idea is to see the influence of the lateral displacement on the vertical loading capacity of a steel pile in soft clay deposit. Next, please. That it is of the structure that was the failures after, I said, 22 years. Next, please. Another view. Next, please. Then what was the idea to understand what happened? That is a soft soil, a section soft soil profile. Then the idea is that is an embankment, that we have a little difference between this area and the other area. Here we have a football area to play. That is very important in Brazil. Then all the time this embankment is little, put something more, because we need to have a very good area to play football. Then the idea is in the soft soil deposit has a very big difference in its thickness. Then the idea is along the time, very slow lateral movement. That is a steel pile, fixed here. Then the idea is the occur a lateral displacement with the time, and the investigation is see how this lateral displacement reduce the vertical load capacity of the steel pile. It's important to understand also that we have a negative friction occur here also because the embankment wasted time. Next, please. That is one lateral load test instrumentation scheme. Next, please. Then that is the predict and measure display horizontal displacement on the top of the steel pipe with inclinometers and the stesometers. Then we have here the measure results and predict by GMT and PMT using nonlinear analysis, and here using linear analysis. Then we can see very good results between this predict and measure, well, we can see in this table. GMT, PMT, measure just on the first load, the difference is something important, but after second, third, and fourth loading, very close the results between predict and measure. Next, please. Then the other point is how this displacement can influence the vertical load capacity. Then we take the critical load for different lateral displacement. Then we can see the using PY curve from GMT and PMT. We can see how is important, how is great the reduction. Then here for around 3 or 4 centimeter, we have the condition to a buckle failure. Next, please. Well, this is the very recent results I decided to show for you because we have some setup effect and prediction of ultimate load capacity. That is in the same area, is a very recent research, is a PhD research that is in conclusion. And we have a instrumentated static pile load test, and I will show you some few results. Next, please. That is the same area. That is the area where we had the structure that failed. Then the 4 vertical concrete piles and the reaction pile also. Next, please. That is the concrete pile installation and the reaction pile installation. Next, please. Here we are putting the instrumentation that you are using and that prepare the load test. That is the load test, compression load test. Next, please. Then here's the results. Then we have here the setup effect. That is just the first complex load test after 60 days. The second, not the second, but the 5. We have this difference between the capacity, load capacity, ultimate load capacity. In other area of Recife, we had a more important setup effect than this place because that is a very, very soft organic and thickness very, very high. And that is the prediction using semi-empirical method, including the GMT from Power et al. 2001 and the PMT. Both are very good prediction for the ultimate load capacity. Next, please. Then the conclusions. The investigation performed in Recife soft clay confirmed the important potential of the GMT in the determination of soil type, geotechnical parameters, and application for pile foundations analysis. The GMT correlations are recommended to be used in Recife soft clay deposits for geotechnical design parameters. The predicted lateral displacement from the linear analysis by using PY curve obtained from GMT or PMT test closely match the result measured with the lateral load test. And the lateral displacement drastically reduced the vertical load capacity of a steel pile in soft clay deposit, and as can be observed through the nonlinear analysis, making possible the occurrence of a buckling failure. And the last one, they predict ultimate load capacity of a concrete pile in soft clay deposit from DMT and PMT method closely match the results measured with the static compressor pile load test. Thank you for your attention, please. And I would like to thank my colleagues that have many colleagues that work in this research. Thank you.
Our story starts maybe 12 years ago, when by fortunate I was in Spain and I saw the Dilatometer for the first time, and I read something about it, and I decided to buy it because it was the best bet I've ever done. Okay. So we started, better saying, doing some experiments on sedimentary soils. But as I live in the north part of the country, and the north part of the country is basically built on portogranite with very complex residual soils, so I decided at the time to take two experimental sites and try to use the DMT on these residual soils. Again, I was very lucky because at the time Antonio Viana da Fonseca was doing his PhD, and it was in the beginning of his fantastic work, and so we developed really a very important relationship on this stuff that made us up to date. So next. This is some pictures of our granite. This is the granite in a very weathered way, but it's not yet the residual soil. Next. This is typically the residual soil block sample that we took in our research program. Next. Some of the problems that we have there with blocks mixed in the middle of residual soils. Next. And the general view of a cut on residual soils. Next. So those are the basic characteristics of the overall work we've been performing in residual soils. It's kind of a soil with this kind of particular arrangement, open voids on a cemented structure. Usually the unified classification points out SCM-SC soils. Void ratios between 0.5 to 0.8, and degrees of saturation between 15 to 100%. The DMT identification, it was very consistent since the beginning with this data, so that was not a problem. Next. The problem was that the general correlations made for the coefficient of earth pressure, shear strength properties, stiffness parameters are very different, and so it was quite a job because everything seemed to be wrong at the beginning. So we had to develop new correlations for almost everything. Next. So the state of stress, we tried at the beginning to use those correlations for granular soils, the Baldis correlation, and then the easy to use Campanella and Robertson to use only DMT, and we have always really high values, so it came up rearrangement of this based on these two correlations, and we changed the In-Situ coefficient based on the relation of DMT and CPTU relation presented by Campanella and Robertson. So it's the point out. How does it works? Like this? No? Yeah. Yes. So what we did, this C2 is typically 0.095. So we rearranged this using this supposed to be the relation between KD and KC over effective stress. So this rearrangement took us to real good values for those values that we are used to have, and for our experience, and for some SPPT tests. Next. So next. You can see the Baldi's K0 DMT, which is this one, is the K0, the K0 from Robertson and Campanella based only on DMT. This is K0 from Baldi, and this is the with that rearrangement of the formula. So as you can see, the K0 came up for the usual values of K0 in these residual solids, we are typically between 0.35 to 0.5, 0.55. So as you can see, it's the results really fit on this within this interval. Next. This is the division, because I try to divide what is based on the M over KC results from Jamiokolsky, Marchetti's references. So the NC sandy soil would be something like MKC around 5 to 10, and from 12 to 24 it would be OC. So I divide both, and you can see that in both situations the results match perfectly. Next. The strength properties, we have a problem there, because we don't have only one strength parameter. We have the cementation structure gives rise to a kind of cohesion intercept. So we have friction angle and cohesion intercept. In the first place, the results deduced from the general formula would point out very high friction angles, because they didn't represent the friction angle itself. It represents the global resistance. But as the dilatometer test is a two parameters test, it is possible to deduce both, and that's what we tried. Next. So first we have to look at the lateral stress index. Next. And the results showed always profiles very stable with depth, but not around 2. Instead, within the interval 5 to 15, that would be reflecting the cemented soils according to Marchetti's consideration at the beginning, taking account of KD. So, okay. Next. So, what we tried was, we thought, and we think we are right, that although the OCR is not something that has a meaning in the residual soils, the break of the pre-consolidation pressure in residual soils would be representing not the pre-consolidation pressure, but somehow the cementation resistance. So We try to we normalize that to the effective vertical stress, and so we came up to use OCR as an approach for deducing cohesion intercept. Next. Okay, I talked this and this. Okay, so this is numerically equal to OCR. On the other hand, KD, as I stated before, clearly showed the presence of a cementation structure, because the profiles were stable but higher than 2. On the other hand, I always try to play more than one test together in the same campaign, so I had a lot of results on CPTUs and DMTs, and I used, since they have the similar meaning, I used the MKT also to try to deduce this cohesion intercept. So this is kind of typical profiles with MKC, OCR, and KD. As you can see, KD is very, there's no peaks at all, it's very stable. So it's the sensing the variations of the cementation, it's not a good parameter, although MKC and OCR, they clearly show the peaks in the, so sensing the variations on cementation structure. Next. So what we did was compare both three. I'm just presenting one. You have the rest on the main paper, but we compared the results with triaxial testing, mostly made on block sampling, and we compared directly cohesion result with OCR or cohesion divided by the vertical effective stress. So, and we came up to this correlation, which is, I think, rather good, although it's not, it's only 7 experimental sites, but usually what happens in all of them, OCR and MKT have the same kind of correlation factors, and usually the correlation is better with C-linear itself and not and a little lower with C-linear over the effective stresses. KD has, of course, as we expected, lower correlation factors. Next. This is a kind of when we go to the friction angle, the first approach was to compare the phi deduced from DMT according to Marchetti's last correlation, and compared with the phi from CPTU deduced from Robertson and Campanella. And so, as you can see, there's a good fit of the data. Next. But usually those, as I stated before, those results reflect the cohesion and friction angle altogether, and so the friction, when you deduce a friction angle, you deduce an higher one because of the contribution of the cementation. Then we tried to compare the difference between phi DMT, that would be the global resistance, with phi triaxial, that would be the friction angle, the real one, and compare with the results of the cohesion intercept, and we came up to these two correlations again, C-linear and cohesion divided by effective stress. So we can then correct the phi from DMT, the feed deduced from DMT and correct in function of the cohesion intercept we deduced before. And when we do so, you can see the real phi deduced this way and corrected this way against triaxial, with both correlations that, as you can see, fit very well. So we think we are pleased on this. We need more data, of course, but we are pleased on and are very confident on this way of doing that. As a reference, I've always point out that we have the results of cohesion over the pre-consolidation stress. That would be the break, would be something like 0.011, which are lower than those deduced by Main and Stewart and Mesri et al. For over-consolidated clays. Next. Stress and strain relationships. Next. Background. So M is, as you might all know, at least those we are familiar with the DMTs, that the information on M is really a very sensitive one, and we think it's because of M incorporates ID, the over consolidation ratio, and the Dilatometer models, of course. So in the case of residual soil, somehow the cementation would be represented here because of KD. Next. AD, of course, represents the ratio between the applied stress and resulting displacement. Next. DMT insertion creates a lower level of disturbance than usual penetrometers, as Bailey and Scott stated in 1975. So M is a good parameter to deduce stiffness properties of soils. Next. So the results pointed out, we've tried two comparisons. One with CPT results. So we used the Lund and Christopherson expression for M, and as you can see, as we expected, the range of variation of the results on M DMT are larger, so indicating more sensitiveness than the results on CPTU. But those are exactly made on the same experimental sites. And triaxial tests confirms they were even higher than the DMTs, but the interval, as you can see, it's more or less it's a good convergence of the both intervals. In two of the cases, not at all, but in two of these cases, Antonio had pointed out in 2001 in Bali conference the direct correlation between G0 and ED, and the 10% E against ED, which are usually, this one is higher than those pointed out from Baldi, and this one is in the middle between the NC and OC soils pointed by the same authors. Next. Now that was something that came up. Our soils are very heterogeneous, so you've got not really soft, but medium compact soils mixed with some horizons very stiff, and we don't have we are not so lucky as you are here in America, and we don't have those kind of trucks. It's not so easy to buy those kind of trucks. So I don't have the pushing capacity that you can have here. So I started thinking that I talked a lot with Antonio about this problem, And we believe that as the dynamic, the insertion of the blade is vertical, while the measurement is made in the horizontal, somehow we could have most part of the properties well measured, even with dynamic insertion. So we tried in 3 or 4 experimental sites. We performed pairs of tests: static, dynamic, static, dynamic. So the first thing I'm pointing out is the relation of N20. Of course, I think that would be we should do some normalization on the equipment, but I try to compare separately the N20 DMT with N20 DPSH. DPSH means dynamic probing super heavy, and the NSPT. So next, those are the basic results. Next, N20 DPSH in this kind of soils is typically this relation. This one was deduced not only for these areas, but globally in residual soils. You perform frequently both of the tests. So we have this N20 DPSH, and next N20 DMT against NSPT, N60 SPT. The real good thing about this is that when you substitute values in here, this one is going to confirm these two. So it's good. It is good to know that. So somehow dynamic insertion. Next. What the results we come up is that all the MT parameters reduced with dynamic insertion except for ID. Next. It reflects using the method that we presented before. We can feel the loss of bonding, which confirms the results of that method. As you can see, this is a typical profile. You see the static insertion and dynamic insertion. This clearly goes down. And the decreasing of stiffness and strength properties. Usually what we can point out in terms of geotechnical parameters is that the friction angle and the unit weight they are not very sensitive, so the results are more or less alike. But the cohesion and the stiffness parameters will really go down with the dynamic insertion. Okay, I'd like to thank to the man who gave me this tie. Thank you.
I'm going to speak about the first experiences we have with flat dilatometer tests. I would like to thank Alenka Robas, who is here with me, who did a lot of testing and interpretation, and my boss, Bojan Majas, for the support in this work. And of course also Professor Marchetti, who in a way allowed us and give us the opportunity to use the equipment and later on have it and do many tests. Can you go? Roger did decide to put this paper in the difficult geomaterials session, and I have to, with this picture, I have to say that he was correct. Maybe Slovenia has only 20,500 square kilometers, so it's a small country, especially compared to the States. But you can see many different colors on this geological map. which in effect is very, it's not very detailed. And the numbers show the meters of dilatometer tests we did so far in 3 years that we use the equipment. The white and the yellow areas are, well, it appears more green than yellow here, are let's say deposits, soft deposits that can be tested by the dilatometer. And we have Alps on the northwest, we have Pannonian level on the northeast, and we have some marine clays in the southwest. And these were, and then we have the, well, around the capital city, which is in the center. Here is the capital city, Ljubljana. It was a swamp 10,000 years ago, and so we still have these marshy soils, very soft, and here we did quite a lot of testing in the marine clays and then in this area. A brief history, let's say more than 25, 30 years ago, only SPT and vein tests were used in Slovenia. Then in 80s, there was a group of people enthusiastic about using CPT, but it was a long time not accepted. Only in 90s, it gained acceptance and is more and more used, and is used even now. We introduced the Menard pressure meter in 96 and in 2001 the DMT. And the last two tests, so pressure meter and DMT, gained acceptance very, very fast. So within a year or two, people were asking to come and to do tests. And it's mainly because we're intensively constructing motorways. Everything is going to be constructed and designed very fast. And of course, in-situ tests allow to do fast testing, fast interpretation, and they proved to be reliable. So we use two pushing methods. We use drilling rigs, we use CPT truck, and in fact there is another set of DMT equipment in Slovenia, but I'm only going to present what we at the university did, and in fact I don't really know how much work was done by the other group. Well, let's go through these results we've got. First, about classification. Mostly we found that the classification, although as stated several times by Dr. Marchetti, it's only a rough estimate of classification through the stiffness of the soil, proved to be very good. For instance, in this example, sand, very good reflected. We can also see some sand which was not given in the core log. So in general, we get good insight into classification. What some people complain about is that we usually get the classification as a sand in the layers, which can be even clay or silt. It is desiccated layers. But this is really, normally this is, or usually this is a marginal point. Well, we have more cases like this. Then the tests around Ljubljana, the capital city, you can see that we have very soft soils, up to about 15 or 20 meters depth. Here is DMT result compared with laboratory tests, and this is a DMT test in the location where which was preloaded, and we clearly see the increase in odometer modulus, very good match. And another location, few kilometers away, again CPT and DMT. DMT catches these sand layers which are definitely present, and CPT only does when this layer has more thickness. Again, few laboratory measurements that can confirm the values. In the marine clay, you can see this. This is the historic city of copper, Capodistria for Italian friends, and this is now the port of copper. So it's essentially constructed on the reclaimed land. And if we compare the undrained shear strength values obtained from DMT and from vein test, we see very good match. The same holds for the modulus. By the way, in the software, in the original Marchetti software, there is another formula for marine clays. I forgot to show this, but it doesn't work, at least not in our case. So the original Marchetti formula proves to be very good in this particular site. We stay in the same location. So this is the picture we've seen before, and this is slightly larger area. So around the city of copper, we have 4 locations where we made quite a lot of testing, and this CU comparison is again from the port itself, and the first one was from here. The other one is on the other side, and again the same soil, the same conclusions. And then I was pleased to see how well the KD represent the actual over-consolidation or the stress history. These are all tests we have made on this in this area, and I only emphasized the extreme 2 locations. The first one with the lowest KD was made here in the water actually, so it is not reclaimed yet. It is still 1 meter in the water, and the other one, the other extreme value is got here, where there was a school built and later on demolished, and because the new school is going to be constructed. So this was reclaimed maybe 100 years ago, and this not yet reclaimed. And in between we have many different sites with different stress history, but definitely KD values are increasing with the time and value of preloading. In 3 years, there were not many possibilities to compare the predicted and measured settlements, but I will show you 2 cases. The first one was, and this was really one of the first tests we made, and made the Class A prediction of settlements, and the prediction was here for the center of the embankment, and for the edge of embankment, it was a motorway embankment 7 meters high. These are the DMT in red, and blue spots the CPT results. The last measured settlement was slightly lower than that, but the consolidation was not completely over because the construction was going on very fast, and they put it into traffic before the consolidation was complete, and so it was not possible to measure anymore. But we did the Ahsoka analysis and tried to predict the final settlement, and these were the numbers that came up. It's well, you can say the fraud, but it isn't. What we often find out is what also Professor Main mentioned yesterday, that on a location that we visited on Monday, there are several groundwater tables, and we have the same situation many times. And what we usually don't know in the routine work is what the pore pressure distribution is, because we think, or we know that in many places we have in sandy layers we have artesian pressure, And so the measured water table in the borehole can be either too low, either too high, but very rarely we will measure what we actually have. And DMT interpretation needs the pore pressures. This is just one case which has, this is the CPT U naught reading, and I mean the penetration pore pressure. So this is the desiccated crust, and here we come into the water saturated layer. You can see that modulus is practically zero, very low values of undrained shear strength, and this was not something that was seen in the borehole. It was not captured by CPT. CPT measured here the value of undrained shear strength around 40, and well, I don't think this difference is entirely due to pore pressures or something like that. It may well be that the variation in the soil ground contributes at least a part of this difference. The data we have on the groundwater level is that it is practically on the surface, but later on we discussed with the people who did the boreholes, and they said, yeah, but we found the water on the 4.8, and then it rose to the surface. And just putting this difference into the software, we see the difference in the modulus and in the undrained shear strength. It might not be significant, but with this low number, everything is significant. So the importance of pore pressures in the interpretation is something that needs attention, and the actual values of pore pressures are important. Well, again, with these desiccated crusts, usually, this is in 90% of cases, we got this very high modulus on the top, which of course is not significant. This is usually only upper half meter or a meter, and it is really insignificant in the interpretation. But in some cases, and this is one of the extreme cases, we got this difference on a depth of nearly 6 meters. And these are the lab values and the CPT value. And in this particular case, I'm going to show the entire case history soon. In this particular case, the design was made before we had the DMT with us, and so the DMT tests were made only a year later or 2 years later, and so the design was based on these numbers. And the case history is again in the close vicinity of the marine clay we had here, and it is about this embankment, which is nearly 12 to 9 meter high. From here on, the embankment was constructed in early 80s, and just at this end, the construction was so fast that collapse occurred when the embankment was 7 meters high. So we had these full-scale test, unwanted, but still full-scale test on the ground bearing capacity, and we knew perfectly that this embankment cannot be constructed without any additional measures. So the construction was well, we first installed the stone columns, and this proved to be efficient. It gave enough strength, or enhanced the consolidation rate, so the construction was essentially or more or less drained, and also the behavior of the embankment now is satisfactory. The DMTs were made when embankment was few meters high at the well, at the edge of the embankment. one test was made further away to get rid of any effects of existing embankment, but unfortunately this third DMT was entirely in a sandy ground, which is not characteristic for the other subgrade here and the embankment, and so we don't mention it anymore. Can we go further? So this is the layout showing the stone columns. You can see that the stone columns are not installed at the outer 8 meters of the embankment. So these DMTs were not that much influenced by the consolidation under a few meters of embankment that was made ahead of tests. The behavior of embankment was well documented. We had here these measuring points for settlements. Even we measured settlements with horizontal inclinometers. This is the schematic cross section. The embankment, stiff clay, 5.5 meters in general, thick, then soft clay, below that 5 meters, gravel. We have the water pressure here in the gravelly layer with the phreatic level practically at the top. So such distribution of pore pressure was taken into account. These are DMT results showing very high moduli in the upper layer. The expected values of moduli here in the lower part. Again, material index, which very much corresponds to the reality, and of course high horizontal stress index, which is characteristic for desiccated layers. If we put together what we had, CPT and laboratory results for modulus match pretty much together, and this is the DMT, and here we have CU, which is in very good agreement with all other data we have. So we were talking during these days also. Can we go slide back? Yeah. We were talking what to do with this, and my first idea was that we probably should make some modification in the equations for modulus, but modifying KD, which is primary factor, can also influence the CU. So the KD is probably just right. If there is something to do, we have probably to think about some further reduction of only of modulus, not influencing KD. But here, because we have stone columns installed, maybe there is another reason for this difference. So please go to the next. We did the analysis of settlement. This is the prediction of settlements from the lab test. This is the prediction for the dilatometer test, and these are the measurements. So we measured 68 centimeters of settlement. The original prediction on the by the laboratory tests is 63, taking into account stone columns. So if we do the same using dilatometer moduli and also take into account the presence of stone columns, we get approximately half of that. The most of difference goes to the upper stiff layer. The settlement in the lower layer is pretty much okay. We had another measuring point. Unfortunately, it was only one, where no stone columns were installed in the ground. And if we make the same analysis there, we see that DMT prediction is in very good agreement with measurements, and that the laboratory results exceed these values. So what can this tell us? It can well be that this desiccated upper layer got in contact with water through the stone columns and reduced in modulus. And so this can be the reason why we have higher deformation where stone columns were installed, and low values, very much in agreement with the DMT prediction, where we don't have stone columns. But it's a pure speculation and hypothesis. We don't have any further proof, and it is just 1 point. So from the case history, we can conclude that, or we can speculate that stone columns may have caused the stiff clay softening. But if this is not the true, maybe we need some further reduction of dilatometer modulus in order to get into this into the range of real modulus. I observed that during Paula's presentation today, she showed us that in the Venice case, the back calculated modulus from extensometer measurements was much lower than the modulus obtained directly by dilatometer readings. And clearly there is some need to further investigation in this direction. The wish in the ground investigation is always to have one tool that could give you all necessary data. This is, of course, wish, but I think that DMT is maybe closest to this goal. Well, and module in non-saturated clay layers seem to be too high, and we need still further research in that. And just as a last speaker, I think that I will share our common interest in continuing to collect knowledge and well-documented experience and theoretical investigation in this field. And I think we should follow with such a meetings we have here, not each 23 or how many years, maybe more often, not only because it is nice to meet all these kind persons that we are here, but also because such a conferences press us to put our numbers together, our knowledge together, and to publish and document this. And I think this is something that make us make progress. And I have to thank Roger for organizing this beautiful conference. So the question was if this upper layer might got influenced by the installation of stone columns. Definitely yes. Definitely yes. Yeah. Yes. Not only just by traffic, but it is the installation of vibratory installation of the stone column. This is also important possibility. Yes.
You made the DMT after the embankment was built. How you make sure that the stresses induced by the embankment have not improved?
They surely did. They surely did. I mean, these DMTs were made for two purposes. One, to get the DMT measurements in this location, but in order to get the money for the measurements, we had to give the useful results. So we, the embankment was monitored because we were afraid of ground failure, and we wanted to. It was done previously by CPT, by repeating CPT measurements after each critical step, and see the CU improvement. And once we've got the DMT, we also did it with the DMT equipment, and the critical lower layer for this lower layer, we've got the same results with the CPT, with the lab test, so we were pleased with that. But the question remained. I don't know if we really much disturbed the upper layer slightly away from the embankment, because it was highly over-consolidated. And as shown previously, in the over-consolidated layer, modulus is not that much affected.
I just want to recall what I think may be an important fact. When you are in a situation of high horizontal stress, which may not be your case necessarily, but anyway, when you have a high horizontal stress, the presence of this horizontal stress is reducing a lot settlements.
Mm-hmm.
Now I think that CPT is not so sensitive to horizontal stresses, but even odometers, the first thing you do when you take an odometer is you put to zero the horizontal stresses, and then you have to regain the stresses when you compress, but which will never be the same as if you had in situ high horizontal stresses. So this could be also a reason why even a very good odometer in OC clay is too low. And I remember an MIT publication by Ladd in which he recalled Terzaghi saying that even in good odometers, in OC clays, the odometer modulus can be 2 to 4 times, to 5 times too low.
Yes.
This was Terzaghi.
No, I'm sure that modulus measured by DMT in such crust layers is, in a way, at least we get the difference, because with CPT we don't have this difference, and the reality is, I mean, you can even feel it when just touching the soil. It's much stiffer, but it is the question of the amount. It's really, I don't know how 5-6 times stiffer, or maybe 2-3 times. So it's there probably is some margin that needs more investigation, especially your well-documented case from Venice encouraged me to show you this, because there you measured settlements each meter along the depth of let's say borehole with extensometers, and compared to DMT modulus, and I think with few more cases like this, we could understand what's going on. Thank you.